So let's work in section 7.3 now on secants and tangents. Now this is again a section with a lot of results that are not used very often. One or two of them are a lot, but some other ones are just rather specialized. So mostly you should just understand the type of problems we're working on here, the type of results we get, and know that if you're ever working with circles and you look at things look like tangent lines and secant lines, then you have a bunch of results about them that you can lay your hands on. Okay, well, a secant line is a pretty simple thing. It's just a line, whoops, that intersects a circle in 2 points. So you just extend a chord. Let me see if I can draw. There's a circle. Don't know why it shows up fat. Let's thin it out a little bit. And then if you have a line that passes, this is a secant line because it intersects the circle in 2 points. Okay, so it's an extended chord. Take a look at a few theorems here, and some of these I'll prove, some of them I won't. Theorem 7.9, if two secants intersect outside a circle, the measure of the acute angle formed is half the difference of the measures of the intercepted arcs. Now think about this. There were some similar theorems we had in the last section when we're dealing with chords here. Okay, so what we want to show, if we have here our two secants intersecting outside of the circle, we want to show that the measure of the angle AEC is 1/2 the difference in the measures of the arcs it intercepts. So the measure of arc AC minus the measure of arc BD. Okay, so I'm going to write this, do this kind of proof rather in kind of paragraph form. Okay, some of the proofs in the book are 2 columns, some of them are paragraph form. So let's do this by, first let's draw. So here's the proof. Let's draw the segment AD. So we've got a line segment here. Let me see if I can make it look a little better. Yeah. AD now is an inscribed angle, and it intersects an arc here. I mean, AD now determines several inscribed angles. Okay. And what we have here is that now the angle ADC inscribes, okay, so angle ADC, this guy here, inscribes arc AC. So the inscribed angle theorem says that the measure of angle ADC is 1/2 the measure of the arc it inscribes, AC. Okay. Similarly, well, that's inscribed angle theorem. Similarly, angle DAB okay, this angle here inscribes arc BD. So the inscribed angle theorem says that the measure of angle DAB is 1/2 the measure of the arc. Okay. So we're kind of getting it here. Notice now that angle ADC is exterior to the triangle we have up here at the top, ADE. So the exterior angle theorem says, so the measure of angle ADC is equal to the sum of the measures of its opposite angles. Angle DAB, actually angle DAE, same thing as DAB, plus the measure of angle DED. Okay. So let's write a few things down here. What do we got here? The measure of ADC. Okay, ADC. This. So plugging in what I know from here, the measure. Let me write everything down again here. The measure of angle ADC is the measure of angle DAE. Well, let's okay. DAE plus the measure of angle AED. Okay. So this angle is equal to the sum of the two remote interior angles. Okay. The measure of angle ADC, I have that this is 1/2 the measure of arc AC. DAE, well, DAE and DAB are the same angle. So this is 1/2 the measure of arc BD plus the measure of angle AED, which is the same thing as AEC. Okay. So subtracting this guy, we have 1/2 the measure of arc AC minus 1/2 the measure of arc BD equals the measure of angle AEC. And we're done here. We just need to factor out 1/2 the measure of AC arc minus the measure of the BD arc is the measure of the angle. Okay. So there's one theorem that you can determine the measure of this exterior angle here by subtracting the measures of the arcs it determines and taking half. Take a look at theorem 710 now. We'll do examples at the end when we'll go back. We've got a lot of material here in this section, so I think the best way to do is to cover all the material, then go to the examples at the end, and then go back and forth and figure out what works where, because it's a little bit confusing because of everything we're going to do. Okay, 710. If two secants intersect outside a circle, then the products of the lengths of the two segments formed on one is equal to the products of the length of the corresponding segments on the other. So what we want to do here is we want to show that if I take AB and multiply that by BE, I get the same thing by taking CD times DE. Now this looks familiar to some of the other things we've had. So it really is. All right, now for the proof. We need some triangles here. Or at least we need some other some angles in the circle here. Let's draw AD. Okay. Okay, you can't read that. Draw segment AD. Okay, so we're going to go from here to there. And let's draw segment BC from here to there. And we consider a couple of triangles here. Now, my proof is a little different from the book. They've got an extra step or two that I really think is not at all helpful. We're going to look at triangle AED and triangle CEB. Okay, so triangle AED and CEB. Now, notice that angle DAB and angle BCD let me rewrite these a little differently here. DAB is certainly not wrong. I just want to think of it as angle DAE and angle BCE, both these angles inscribe that arc, or intercept, I don't think, not inscribe. Intercept arc BD. Okay. And then if you go back and look at corollary 7.2, when you have the situation when two angles cut off the same arc, then those two angles are congruent. By corollary 7.2, angle DAE is going to be congruent to angle BCE. Okay, so this angle and that angle are the same. Now, of course, angle E is congruent to itself. Angle AED is, of course, congruent to angle CEB, because they're just two different names for the same angle. Okay, and this would be like the reflexive property to say an angle is congruent to itself. Okay. Now, I have two triangles here. I have triangle AED and triangle CEB. Okay, and I have two angles of one triangle being congruent to two angles of the other. So this is the AA similarity theorem. Okay, then I know that triangle AED is similar to triangle HCEB. Okay, and since they're similar triangles, we have proportional sides. Okay, so hence, let's see how I'm going to do this. I'm going to say A had to pause there for a minute because I had something written down wrong. My proof is fine. It's just I have to make a correction here. This is not what I'm trying to prove. Okay. I'm trying to prove the product of the lengths of two segments formed on one sequence. Okay. So this is going to be AE times BE, not AB times BE, equals CE times DE. Okay. Okay, everything in my proof's right. I just had the wrong conclusion there. Sorry about that. So let's go back. I realized that in the process of proving things, I wasn't going to get this result. So I had to go back to the book and realize, well, I just copied the conclusion down wrong. Anyway, since we have shown that these two triangles are similar, then corresponding sides are in proportion. That means that side AE divided by side CE is going to be the same thing as side ED divided by side EB. Okay, so multiply to get rid of the denominators, okay, which some people call cross multiplying. What you're really multiplying by is CE times EB. Okay, so when you multiply on the left by that, the CE's cancel. You have AE times EB. When you multiply on the right by that, the EB's cancel. You have ED times CE. Okay, which is what I want. I have some of the letters backwards, but that doesn't matter. EB and BE are the same number. DE and ED are the same distance. Okay, so I proved that. So no, I don't want to prove this. This is what I want to prove. Okay. Now, a tangent line. A tangent line is a line that intersecting a circle in one point. This is called the point of tangency. Okay, so it would look something like a thin circle here. It'll look something like, I'll put it here. Got it. There is a tangent line because there is one single point where they intersect. Now we have, whoops, an important theorem here. This is one you should know. You should have this theorem memorized, okay, because you're likely to use it a lot. You may have even been called on to use it in calculus or so. It says a radius or diameter of a circle is perpendicular to a tangent line at its point of tangency. Okay. Now, the proof of this is not a standard sort of proof. You really can't do it in a two-column format. This is going to be an indirect proof here. Okay, so let's look at our picture here. Here's what we're going to say here. Suppose line L is tangent to circle O at point P. We want to show that it must be true that OP is perpendicular to L. Okay. Now we're going to prove this indirectly. We're going to use a proof by contradiction, whereas we're not going to actually show that it's perpendicular. We're going to show that it cannot be not perpendicular. So this is an indirect proof, also called the proof by contradiction. Okay, so we're going to, let's assume that L is tangent at P and that OP is not perpendicular. To line L. We're going to show that this is impossible. That if it's tangent to P, it must be perpendicular because it's impossible for it not to be perpendicular. Okay, first thing before I get too far into this is note that if L is tangent to a circle, okay, then no point of L can be inside the circle. Okay. If there's a point of the line inside the circle, the line's going to go off in infinitely long in two different directions. It's going to intersect the circle more than once. So let's remember this thing. Okay, this is actually going to be where the impossibility shows up. So remember that. Okay, so let's suppose that L is tangent and OP is not perpendicular. Okay, then there's some point Q on line L where OQ is perpendicular to L. And this is going to look funny because what I'm trying to do is to draw an impossible case. Okay. But somewhere there's a point here. If it's not P, it has to be a point somewhere, Q, where I have a perpendicular here. OQ is perpendicular to L. Okay, now, yeah, I know it looks funny. Triangle OQP is a right triangle. Okay. And even though it looks kind of funny here, OQ and QP are legs, and OP, which is opposite the right angle, is the hypotenuse. Okay. Now the hypotenuse is the longest side of a right triangle. OP then is greater than OQ. Okay, okay. I know what it looks like here, but OQ is one side of one leg of the right triangle. Okay. OP is the hypotenuse. This means, okay, since OP is a radius of the circle, okay, this means the Q actually has to be inside the circle. Because it's a shorter distance. Well, this is impossible. Q is a point on the tangent line. So it cannot be inside the circle. So our assumption that we made here is impossible. If L is tangent, at point P, then OP must be perpendicular to L, because it can't be tangent and not perpendicular. Okay. All right, now we're going to have a quick couple of theorems. Okay. I'll do a sketch of theorem 712. The measure of an angle formed when a chord intersects a tangent line at the point of tangency is half the measure of the arc intercepted by the chord in the tangent line. So what we're saying here is the measure of angle ABC, this the formed by the chord, okay, is 1/2 the measure of arc AB. Now, this should sound a little bit familiar because it's a whole lot like what we had the inscribed angle theorem, isn't it? So a sketch of the proof. Proof is all in there. Is let's draw a diameter through from point B. Point B. So we'll draw a diameter which is going to look something like this, and let's give this point down here a name, D. Okay. Now what we just proved is angle CBD is 90 degrees. Okay. Now notice that that's 1/2 the measure of the arc we're talking about here, from D through A to B, because that's 180 degrees. Now, what we're really looking for is the measure of angle ABC and the arc that is determined by that. And let's see, we notice that the measure of angle ABC plus the measure of angle ABD is the measure of angle CBD, which is, okay. And let's see, the measure of angle ABC plus, okay, ABD is an inscribed angle. It intercepts arc AD, so this is 1/2 the measure of arc AD. And we just said CBD over here was 1/2 the measure of the DAB. Okay. So the measure of angle ABC, you subtract this, it's 1/2 the measure of arc DAB minus 1/2 the measure of arc AD. Well, you take DAB and subtract off AB, you get the measure, subtract off AD, you get the measure of arc AB. Okay. This arc minus this arc leaves us with that one. Okay. So it should have a few more words or so on it, but that's the main idea about the proof. Is drawing the diameter. Now you have an inscribed angle you can work with. It doesn't really matter that this is 90 degrees. What matters is that this is 1/2 of that thing. Okay, a couple of theorems here that I'm not about to prove. Their proofs are done in a book. These are tangent versions of the secant theorems we did a little earlier in the section. When a secant and a tangent line intersect outside the circle, the measure of the angle formed is 1/2 the measure of the larger arc minus the measure of the smaller arc. The very same thing as if we had two secants. Okay. 714. If two tangent lines intersect outside a circle, the measure of the angle formed is 1/2 the measure. Okay, here all we're doing is we're taking the previous problem and taking this secant line and we're moving it until it becomes a tangent line. Same thing. So let's go on down. And here's a good corollary here. This is an important result, 715. If two tangent lines are drawn to a circle from the same point in the exterior of the circle, the distances from the common point to the points of tangency are equal. Okay. So what we have here is we have AP and BP are tangents, Okay. P is the exterior of the circle. We want to show that the length of AP is equal to the length of BP. Okay. Now this is actually the proof here is number 31 in the exercises, so I'm going to do this rather quickly here. Let's draw some segments, AO, BO, and PO. So we're going to draw this segment, and this segment. Okay, let me see if I can get these guys in a little better shape here. Okay, that looks a little better. Okay, what we know here is that AO and BO are the same length since they are radii. Of this circle. Okay. We also know that angle OAP is 90 degrees, which is the same as the measure of OBP because of the previous theorem. Okay, well, back here a little bit. Theorem 711. The radius is perpendicular to the tangent line. Okay, so this is a right angle, and this is a right angle. And of course, these two things are equal. That's 711. Okay, and OP is congruent to itself. Okay, actually, what I should have put up here is congruent. Okay, so I have two right triangles. And I have a hypotenuse and leg of one. It's congruent to the hypotenuse and leg of the other. By the hypotenuse leg theorem, triangle OAP is congruent to triangle OBP. And I have to pause and take care of my cat. He's up on the desk with me here. And if these two right triangles are congruent, and you can't read that, let me back this up a little bit. By the hypotenuse leg theorem, okay, the right triangle OAP is congruent to the right triangle OBP. Okay. From that, we have that the corresponding sides that AP, hence AP and BP are the same length. Corresponding parts. Important little theorem to remember there, and it's also something I saw in a Praxis 2 review book one time. Okay, Theorem 716. I'm not going to approve Theorem 716. It's just a version of the previous theorem we had back here. Oops. Back there, Theorem 710. Theorem 710, I had two secant lines. In 16, I have one secant line and one tangent line, but it's the same thing here. Make sure you read through the examples in this section. Particularly, there's a nice example, 713 on page 389, that you ought to take a look at. On 391 in the book, you have a big page that summarizes everything that's happened in this chapter. Okay. And they have the major results here from the point of view of angles and arcs measure, and also from point of view of lengths of sides of things. So I'll be working some examples here, and I'll go back and forth between page 391 and so on to figure out what I'm working on. Okay, oops, wrong way. So let's start by looking at number 3. This is on page 392. We have this figure, which works for all the exercises 1 through 6. And then this one, AC is 10, AB is 4, DE is 3, find EC. Okay, so let's put in what we know here. AC is 10, so that's the big length here. AB is 4. Okay. DE is 3, and we're out to find the big length EC. Okay, so turn back to page 391 and take a look at what we got here. Now 391, the top of the page has these sorts of headings. It draws a figure that is probably useful here. We've got the angle measure information for that figure, and then if it deals with segments, lengths, we have that one. Go part of the way down the page and you see this figure. What we've got in this problem are intersecting segments. And we're not interested in the angle measure in this one. We're interested in the relationship between the segments. Now the difficulty here is it's all labeled differently. Okay, so if I want to use this one, I have to put the A's, B's, and C's and stuff in different places, perhaps. Okay. So the equation that we're using is this equation, but it should be AC times BE, not BC, times BC, because C and E are in different places. Okay, and that's equal to CE. Okay, CE here would be the long one, so that'd be EC, and DE is from the here to the, so it'd be DC. Okay, so DE in the picture down here is that little piece which corresponds to DC on our picture. So let's plug in what we got. AC is 10. BC, excuse me, I don't have, but AE is 4, so BC has to be 10 minus 4. EC I don't have. Okay, and the best I can say here is DE is 3, but that corresponds to DC, which is going to be EC minus 3. Okay, so this is 10 times 6 is EC squared minus 3EC. This is 60, so okay. So that's a quadratic equation, which unfortunately does not factor. So we're going to use a quadratic formula. I'd rather do that than try to complete the square. So EC is negative of negative 3 plus or minus the square root of negative 3 squared minus 4 times A, which is 1, times C, which is negative 60, so it's plus 240, 4 times 60, over 2. So it's positive 3 plus or minus the square root of 249 over 2. Okay, we're talking about distances here, so it's going to be a positive number, and so EC is going to be 3 plus the square root of 249, all divided by 2. Okay. A little surprising answer that you had to do all of that. A lot of times they come out evenly, but this one sure doesn't. Okay, let's do a few more here. Number 7. Refer to the following figure. Point O is the center of the circle. Okay. Now, OED, this is this angle. That's the same as ABE, this angle. Okay. BEI bisects OED. What's the measure of arc length BD and angle C? Okay. Well, let's work on this a little bit here. This is a 90-degree angle, right there. Okay. The measure of the arc length of AE, it's the measure of its central angle. So this is 90 degrees, period. Okay, now, angle ABE inscribes that angle. Okay, so this intercepts it or inscribes, actually it's the other way around, but it inscribes the arc length AE. So the measure of angle ABE is 1/2 the measure of that arc length, which is 1/2 of 90 is 45 degrees. Okay. So this angle is 45 degrees. Okay, the measure then of angle BED is, okay, so this thing, well, that's 1/2 the measure of angle OED. OED and ABE are the same size, so it's 1/2 of 45. 22.5 degrees. Okay. All right, now what I want is the measure of this arc here. I know that the measure of angle BED is 1/2 the measure of the arc that it determines. This is by the inscribed angle theorem. Okay. So the measure of the arc length is, well, half the measure of arc length is 22.5, and that says that the measure of BD is 45 degrees. Okay, well now I think I'm ready. Okay, because we go back to this theorem, 7.9. Two secants intersect outside a circle. The measure of the acute angle is half the difference between the measure of the intercepted arcs. Okay. So way back here. Well, actually, it's this thing right here. Yeah. Okay. So the secants are AC and EC. So the measure of angle C is 1/2 the difference of the measure of the arc AE minus the measure of the arc BD. This is 1/2 of 90 minus 45. Okay, let's see, I'm going up to here now. One half of 45 degrees, 22.5 degrees. Okay, took a little while. But we had to use just about everything in that picture. Okay, number 16. Number 16, this is the figure. PQ is 55 degrees, so that's this arc. Okay. PT is 31 degrees, that's this arc. Okay. And find the measure of TUP. So we want to find the measure of this angle. Okay, and that refers back to, we have a secant and a tangent line. Okay, intersecting tangent and secant. And that says the measure of angle TUP is 1/2 the difference between the measure of, in this case, PQ minus the measure of PT. One half of 55 minus 31. These are all degrees now. That's what, 24 degrees? It's 12 degree angle. Okay. Number 24. XY is a tangent to circle O. If OZ equals ZX and XY equals 6, find the radius of the circle round to the nearest hundredth. Okay, let's put a few things in here. We're after the radius of the circle, so let's call this R. And that's going to be here, it's going to be here, and since OZ equals ZX, that's going to be there as well. Okay, now, XY is tangent to the circle at O. When we have a tangent and a radius, we have a right angle. All right, and XY is 6. So what we're looking at here is a right triangle. One leg is 6, the other leg is R, and this third leg is 1, 2, 2 R's. So Pythagorean theorem says R squared plus 6 squared equals what you get when you square 2R. So R squared plus 36 is 4R squared. 36 is 4R squared minus R squared, 3R squared. Okay, divide by 3. You get 12 equals R squared. 12 is the square root of 12 equals R. And that's going to be 3.46 approximately. And we have some inches there. Okay, finally number 25, which isn't near as hard as it looks like it might be. Here on number 25, they say triangle ABC is isosceles with the inscribed circle as shown. AB equals BC equals 12. Well, they could have just said that and not said isosceles. AC equals 7. So this length down here is 7. And we want to find AP and BQ. AP and BQ. Okay. Now, this is an isosceles triangle. So this angle and this angle are the same. Okay. Now, because these angles are the same, then those two sides are the same, those two sides are the same. So in other words, AP equals RC, excuse me, AP equals AR, and that's one of these last theorems we had, but that's also equal to RC, which is equal to QC. Okay, now if since AR equals RC, then that's half of 7, so these are 3.5. Okay. And BQ then, this is 3.5, is 12 minus 3.5 is 8.5. Okay, so there's section 7.3 with a number of examples. I hope this can help you with the homework if you need it. Not too much left to do in the text. We have one more section in this chapter, which is constructions, and I really don't know how I'm going to be able to do a video on that. Then we're going to do a section or so on transformational geometry, reflections, rotations, and translations. And then we're going to do a section on some non-Euclidean geometry. And that will be it for the course.